I have a gyroscope, which is essentially a disc that's pretty heavy and is on an axle, and most of the mass of the disc is towards the outside to give it high moment of inertia. When I pull on this, there's gears there that make it turn and spin counterclockwise when viewed this way, and then I have a string on this end which is connected to this end of the gyroscope. I'm going to pull on it, we'll view it from the top view and view its motion. You can see from the top that it's making a motion, a circular motion. That's called precessing. A side view of the same experiment. In this problem, we're going to consider a gyroscope, and we're going to assume that it's supported on one end here, and the support is such that the support doesn't allow the gyroscope to go this way, up or down, or in and out of the board. So there's a force, we'll assume, that's in each of these directions that prevent that from happening. We'll also assume that there's no frictional forces that create a torque that slow this from revolving or slow it from spinning. So we could solve it, assuming that if we knew the torque that was acting there, but for this problem we're going to start out assuming we don't have those in existence, and I'll make the problem a little bit easier to solve. So there's our here's our system. We have a gyroscope, and it has the disc and this axle are spinning at an omega about the center axis of this gyroscope itself, and we'll have it defined that the distance from the support to the center of the mass of the gyroscope is r. Now, and let's draw the free body diagram, and we'll do it in different views. So looking at it from the side, so here's all the forces that act on here. We'll have the gravitational force pulling down to the center of the Earth, and then we have these three component force vectors which are at the support end. And here from the top view now, we got the same gyroscope. The force is, the X shows it's acting downward. And then I have the same three component forces. And we're going to assume that this gyroscope potentially has some frequency that it's precessing around this center fixed point. And then as far as for our system, obviously for our system we're going to pick just the gyroscope, and the surroundings is everything else. We are going to define our coordinate system so that the x-axis corresponds is the direction from the center of rotation to the center of mass. And let's make our problem a lot easier to solve by having that coordinate system. So if we would have had it up here, then I would have had my x direction running this way. But the x direction is not moving. The x direction this is a inertial coordinate system, but it is fixed to the Earth, not moving with this. But essentially we're going to say at this moment of time, when this is moving around and spinning, I'll take a snapshot and I'm going to put at this exact moment of time, I'm going to have that axis defined right here. So there's my free body diagram showing all the forces and then showing this precession frequency. I'm now going to talk a lot about velocity, momentum, and angular momentum. And we're going to spend a lot of time understanding all the components of those. And that's going to help us to learn to solve for forces and for torques. Because we know that changes of momentum are related to forces, and changes of angular momentum is related to torque. So we'll let's start talking about, again, here's the top view. This one was the forces. Now we're going to talk about momentum and angular momentum and velocity. So top view, this gyroscope from the top view, it's precessing around. So a later time I might see that gyroscope, it might look like you know, it's moved to there. So the center of mass is moved to there. So this gyroscope is potentially precessing from a top view like this. And since it's fixed here, this radial distance from the center of rotation to the center of mass, that magnitude, that length magnitude of r is staying constant. So so now what I have is from the top view, essentially, well, this gyroscope from the side view is precessing around, is staying on a plane. So the center point's there and it's spinning around, and it's on a flat plane. So in the top view, we're down to essentially a two-dimensional problem on the top view as far as looking at motion, because there's no motion in and out of the board. So what's the velocity of the center of the mass? It was here, it moves to there. The velocity is perpendicular to the motion. The velocity of the center of mass is perpendicular to the motion, as it was there, and then it'll be there. And then we know that the velocity of the center of mass is, due to precession, is this radius times the angular frequency. And the angular frequency, precession was capital omega. So we'll have a velocity of precession, which is r omega, capital omega. For momentum, then, here's the most broadest definition of momentum. For this problem, we'll assume that this velocity is very small relative to the speed of light in a vacuum, so that gamma will go to 1. So essentially it's mass times velocity. Velocity is here. So this is our momentum magnitude, mr times the precession angular frequency. And this is in the same directionality as the velocity. So the velocity is this way, so it's on this plane, and there's my momentum term at this point in time. And then it's helpful then to consider what's happening to momentum at a later point in time. So at this later point in time, the momentum term would be, again, it's something revolving. The velocity is here, so therefore the momentum is there. And now for this problem, we're talking about, we're concerned about rate of change of momentum as a function of time. And this momentum term can, if it's speeding up or slowing down in the direction in this, so let's call this this is the p hat direction. That's the unit vector direction of p at this moment of time. So it's that direction, and later on it's this direction. So we know one thing for sure, we know that the directionality of the momentum vector is changing with time. So therefore the derivative, it'll have a derivative change in the directionality with time, and also could have a magnitude change. And so at any moment of time, if we define this momentum vector, it's the magnitude times the directionality of it. And then since it's rotating about a circle, there's an easy way to solve for it. And this is using our calculus, our product rule. We can solve for it, and we learn that the momentum change versus time, well, the magnitude can change versus time in the p hat direction. So that's one possible component. So I'll draw that right here. So this is in the parallel direction to its motion. This is that component rate of change of momentum versus time. And then for a vector which is circling and changing directionality, it starts out here and it's going to here. We know that there's a vector then pointing towards the center, which is the rate of change of momentum versus time, perpendicular to its present p hat direction, which is always going to be the magnitude of p at that moment of time times the angular frequency that this p momentum vector is changing. Well, that momentum vector has the frequency, same frequency as this gyroscope. So that's the angular frequency that goes along with this term. And it's that change vector is in this direction. So this term right here is pointing towards the center direction, or here it's pointing to the center direction as well. So now we know momentum, and we have understanding of both its magnitude and its vector. Now thinking about angular momentum, because that we're gonna use that when we solve for torque. The broad definition of angular momentum is well, first of all, for angular momentum we have to think about angular momentum about what? It has to be angular momentum about a point, because angular momentum is not a constant. It changes depending on where you say it's about. So this system from the top view, it's rotating about the center rotation. So for cases where I'm rotating about a center point of a rotation, it's very convenient and it makes the equations much easier to solve if I do my angular momentum with respect to that center rotation. So the point I'm going to pick is the center rotation. I'm going to solve it that way. Alternatively, another good point that's often very good for helping to make the problem simple is to do the angular momentum about the center of mass. I'm not going to solve it this way, but I can probably do that in a future follow-up video to solve the same problem considering angular momentum about the center of mass. But those are two very convenient points that help make the system a lot simpler to solve. So now we picked the point that we're going to do the angular momentum about. We call it the center rotation. And we know there's two parts to any angular momentum. There's a rotational part and a translational part. So for rotational parts, you have to think of two things. You have to think, consider its rotation has no subscript, because rotation means rotation about this own system center of mass. So it's not relative. Doesn't matter if it's about CR or the center of the center rotation or center of mass. This term, the angular momentum of rotation, is by definition about this own system center of mass. So you think this system, does it relative to its own center of mass, does it have any rotation? Well, it does. I mean, one rotation it has is we know that it's rotating here along the center axle of this part. At this moment of time, it's spinning with an omega term here. So that disk does have, I mean, this disk is spinning here, and that's a spinning relative to the center of mass of this part. So that's going to provide us with a rotational angular momentum term. And then, is there any other terms as far as rotational? Is the center of mass rotating at all? Well, if you think about it, this object right here, it's at this orientation from a top view, and then later it's at this orientation right here. So relative to its own center of mass, forget about it that it's translating, that that center of mass is moved. I mean, there is a rotational top view rotation about its center of mass. Here it's pointing there. Later on it's going to be pointing this direction. So it's flipped from there to there, and then it's flipped to there. So there's a rotation in the top view. So there's going to actually turn out to be two rotational angular momentum terms. For each one of these terms now, which are components of the angular momentum about center rotation, we need to concern ourselves and understand both the magnitude and the directionality of these vectors. So first solving, we'll do them independently. So first considering ourselves with this object rotating about this central axis. So let's do magnitude first. So magnitude of rotational inertia is the moment of inertia about that center of mass as seen by this rotation. So this is the moment of inertia around this central axis of this. Okay, and then it's multiplied by the angular frequency that this part is spinning. So that's the magnitude of this term. So that's the magnitude. And then the question is, what's the directionality? So for that, we're going to use the right-hand rule to determine directionality. So we have this thing spinning like this. So for this term, it's spinning this angular frequency little omega, and so my L rotation vector is in this direction. If I had it spinning in the opposite direction, if it was spinning this way, then my right-hand rule would tell me that it would be this direction. But I've chosen to make omega this way, so that's my L direction. And then question is, as this is precessing around, so now at this moment of time right here, it's still spinning in this direction. At that moment of time, this vector is now changed to there. So it started out in this direction, and at this time later it turned to this direction. So I can see that there's we know there's going to be a derivative term that's both going to be in the direction of this based on the magnitude, and I have a direct derivative term which is perpendicular to that. And just as I could solve it for right here, I can do the same thing here, that this angular momentum term right here is changing. At this moment of time, the angular momentum is the magnitude times the directionality, so this is the L hat direction, and I have a component which is also in the L hat direction, which is how the magnitude is changing, and I am turning this way, so I have this component, which is instantaneous, which is magnitude at that moment, times the frequency that this is turning, and just like the momentum term was turning at this frequency, so is this term turning at this frequency. So that's the magnitude of this vector in this direction, and that's going to be perpendicular to the instantaneous direction of L hat, so it's in that direction. So there's my angular momentum term, there's my rate of change of angular momentum parallel to it, and there's my rate of change of angular momentum perpendicular, just considering this term alone. So now let's consider the next term. Again, from the top view, we have this thing rotating this way. So it's spinning like this. Okay, so it's spinning like that. So something's spinning like that. I can see that it's the angular momentum direction is going to be out of the board, but its own center of mass. So I know this one is the vectorial direction is here out of the board, and then right here at this position it's spinning about this point right here. Well, you consider it spinning about its own center of mass. So it's spinning about its own center of mass. So that's also out of the board. So it's out of the board here, out of the board here. There's no change in the directionality of this vector. So the only thing that can potentially change is its magnitude. So what is this magnitude? It's from this top view or side view. I guess we'll call it top. From the what's as seen by the top view. What's we can solve. We'll have to have some information about the geometry of this gyroscope, but what's the moment of inertia about the center of mass in this top view? And that's different than this. It says resistance against spinning in this direction. This one was resistance against spinning this along the axis. So those are two different moments of inertia about different views. And then that's that moment of inertia times the angular frequency. And where here was the angular frequency about spinning in that direction. This is the angular frequency about spinning this way, which is capital omega. So now we know this term, and we know that both its magnitude here is in this direction, and potentially its only rate of change is in this direction. It has no component this way because that vector is not changing. So now we know everything about this term, this directionality, its magnitude, and its derivatives versus time. Now let's consider this term. This term, translational, remember, is consider everything boiled down to a point mass loaded at the center, and it's R cross P. So what does that mean? So R is a vector that has magnitude and direction, and it's from this center rotation to the center mass. So there's my R vector. And then the P is the momentum of the center of mass, so that's going up. So R cross P. So I know that this vectorial term is once again, coming out towards me. So it's going up. So it's pointed upward direction. And then at this moment of time, the R cross P again is pointed up. So at both moments of time, this vector is pointed up. So there's no directional change of this vector. So the only thing that's changing is magnitude. If it's speeding up, if the p term is r's term, magnitude is constant, that term's constant. This term may be changing. This may be changing. So now we know directionality of that, and then at any moment of time, this r and the p vector are perpendicular. So the sine of the relationship angular is 90 degrees, so it's 1. So here's the magnitude of this term. We know p, center of mass, we got it from here. So r times mr capital omega, angular frequency, because we know that that's how that p vector is changing. So coming in here, I can see that's mr squared, angular momentum. Now we have an understanding both of the magnitudes and the directionality of all these components of the angular momentum about the center rotation, and we understand about the momentum and the rate of change of momentum and the directionality of all those vectors. We're going to use momentum now to solve for motions and some forces. And the two momentum things we know are that we know that vectorially that the change of momentum versus time is equal to the net force on a system. Our system is the gyroscope. We also know that the change of angular momentum of any point is the net torque around that point. And we're going to start looking in the z direction. And so this component term, we can think just in the z direction, the angular momentum about the center rotation in the z direction, and the net torque of that center rotation in the z direction. So we'll start with this term, looking at the net torque. The net torque, so torque is r cross f, where r is the distance, or is the vector from this point we're choosing, we're going torque about the center rotation to where the force is applied. So here's that r from the center rotation to where force applied. This force is mg, using these are perpendicular to each other in my case. So using the right hand rule, r cross force gives me a vector into the board. Or you can see it from the top view. Here's my r, and then this force is going down. So r cross mg is going in the minus, this force is in the minus, this torque is in the minus z direction. And there's this magnitude, the magnitude of r, the magnitude of the force is mg. So our force is r, which is that distance, mg, and it's in the minus z direction. So there's this net torque around this center rotation in the minus z direction. And now looking at all the, we had all these terms previously for change in angular momentum, and now we're only concerned, the only one that we're worried about is in the z direction. So from the top view, that's something that's working either this way or this way in that direction. So it's not this magnitude change here, that's that's perpendicular to that, but this term right here, we can see is in the minus z direction. So this is a component of angular momentum with respect to time, and it's of this magnitude, and we know, since it's turning this way, it's also in the minus z direction. So that took care of this term. These terms, we recall that the derivative with respect to times are pointed out of the board. So there's nothing there in the z direction because they're in the y direction. And the same thing for this. This rate of change here is also in the y direction. So the only term right here that's any z component is this term right here. And now substituting in for, we know the magnitude of angular momentum or rotation of this thing spinning is the moment of inertia about the center axis times the rotational frequency, the angular frequency of that, so I omega, and then so this all together, there's my terms. Turns out both of them are negative, So you can cross that out and we can solve for the angular precession frequency, which says yes, it truly, if something is spinning this way, it's going to have an angular precession frequency this way, as in the vector direction as shown. And it's going to have, and the magnitude of that is the r, which is the distance from the, r is simply the distance from the center of rotation to the center of the mass, and it's times the mg, and divided by the angular momentum of that about there, which is the I around the center mass of the axle times the frequency. So the one thing we can see about here is, so as that frequency is slowing down, so if this thing's just spinning and it starts to slow down, then this number becomes smaller and the precession frequency speeds up. So if this thing's spinning at a certain precession frequency, as friction here would start maybe slowing from down, spinning around, it would start to spin faster and faster. So there's a solution for precession frequency, and now we might want to maybe look at a force, for example. So let's look at, maybe try to solve for this force at that support here in the x direction. And for forces, we're going to use this equation. Once again, we're doing it vectorially. So we're going to look just in this is the x direction as we defined it. So in the momentum in the x direction, derivative with respect to time is the net forces in the x direction. We said momentum at this point of time is in this direction, but it has a rate of change, but that vector is changing, is rotating, so it has a rate of change momentum perpendicular is pointed this way, and the minus x direction is the magnitude of momentum times the precession angular frequency, and it's in the minus x direction. From my free body diagram, the only force I have acting in the x direction is the force of the support in the x direction, and that shows positive here, so I put it here, and I can solve for it. And I also substituted, we know momentum is this term, so put that in there, and so we can see that the force is minus m r precession frequency squared, and it's going to be a minus, which means that I drew this wrong, that in actuality this force is in the opposite direction from what I showed. That's essentially what the minus says. So this is a simple solution showing the power actually of picking center rotation as the point I do angular momentum about, because it makes solving the problem very easy. And also very important to remember that even though you did all these things, you always have to consider things vectorially. In this video, I will pull the gyroscope so the disc rotates in a clockwise direction. You can see that the precession is also in a clockwise direction. If I pull on the cord so the gyroscope disc rotates in a counterclockwise direction, as seen from the top view, it will also precess in a counterclockwise direction. If you play with the gyroscope, you can see that the precession frequency is going to be independent of the tilt angle. It just depends on the speed. As it slows down, the precession frequency increases. It's speeding up in precession frequency. A gyroscope that's tilted rather than horizontal further highlights the importance of thinking of things vectorially. So we're going to have this gyroscope, and I'm assuming it's tilted at an angle beta relative to the vertical. And so therefore this distance from the top view is, instead of r, is going to be r sine beta. So essentially r sine beta becomes here, that value. Now we think about what happens to angular momentum. And most of the angular momentum terms now can also include a sine beta term, and let's think about that. And we know for here solving here, the one that's important and one that's still going to be important is this rotational angular momentum about its own center axis. So as at this moment of time, it's rotating here. It has this term right here is this magnitude right here, and that has two components. It has one in the x and one in the y. And this was going to be this magnitude sine of beta, and this one would be this magnitude cosine of beta. And think about this term from the top. So as this part's rotating, what happens to this y term? And maybe think about it in the top term. So it goes to there to there. This y term doesn't change directionality. As this now tilted gyroscope is precessing. So this term has there's no d angular momentum dt term. Well, it becomes zero because this term is always pointing upwards. There's no angular component. So, but this term right here, again, this term with now sine of beta is that direction, and as I wrote precess around right here, this term does have this term right here changing. So when we think about our equation up here, the change in the z direction, now only the sine of beta term is required right there. The cosine term doesn't change directionality. So you can see how this part of the equation changed. Now thinking about torque, so this side of the equation, the torque in the z direction. So torque is r across the force, and so there's my r across the force, and you can see now there's the angle beta between. So it's r, so r force sine of the angle between, which now is this. So you can see that this term now has a sine of beta, and that term has a sine of beta, and ultimately they don't matter. So you can see that the precession frequency is independent of the tilt angle.